hear me? Sweet. Yeah, good morning. Welcome to the Evolutionary Theory session, 9 a.m. My name's Matt. I'm going to be the chair and open things off with a presentation on some work I've been doing with my PhD supervisor, Sally Otto, and collaborator at Michigan State, Chris Klausmeyer. So, environments change. We all know this. Classic example is the world is generally warming, and will continue to do so at a fairly rapid rate, as shown by this IPCC temperature forecast for the next 100 years. And as evolutionary biologists, we all know that populations are able to adapt to new environments. A classic example being ectotherms evolving to be different body sizes. So generally, small individuals do best at warm temperatures, large individuals do best at cold temperatures, and when we go out in nature and we take individuals and we bring them back to the lab, we put them in a bucket, and we warm that bucket up, we consistently see the evolution of smaller body sizes. Some of this response is plastic, but some is evolution, some is genetic, and that's what I'll be focusing on today. But we also know that nature is not one species in a bucket. It's many species in a big bucket, more or less. And this is important because when you have many species, you have species interactions. One ubiquitous one being predator-prey. And predator-prey interactions are going to be very important for adaptation for two reasons. The first and most obviously is, by definition, predators remove their prey. They eat their prey, and there's a demographic pressure on the prey species. Secondly, and perhaps more subtly, predators often prefer prey types with particular trait values. And so, in this case, we have a back swimmer prefers to eat the larger Daphnia, and thus imposes a selective pressure as well as a demographic pressure on the prey. Now, there are many people, many studies that look at the evolution in predator-prey systems. There's many studies on single species adapting to environmental change. But there are much fewer studies that look at the interaction of these two factors and how species interactions affect adaptation to environmental change. There's one recent exception, and a very good one, I think, by Michelle Tseng and Mary O'Connor at the University of British Columbia, who Michelle took Daphnia from ponds around Vancouver and put them in buckets and warmed those buckets up, and warmed one bucket up and kept one a little cooler, and she saw after 8 generations that the populations in the warm bucket evolved smaller body sizes. And so the nice thing about this study is she then repeated that when there was a predator in the bucket with the Daphnia, this midge larvae. And what she saw was quite remarkable, is that the predator, in both cases, the predator caused a reduction in body size. And this is particularly interesting in this warm scenario because we think that smaller body sizes are adaptive in warm temperatures, and thus the predator may be helping the prey adapt by causing it to evolve yet smaller body sizes. And supporting this idea, the fact that this population with predators actually had the highest growth rate. But adaptation and growth rate are one thing, but when we think about adaptation, we're often interested in adaptation because of the implications it has on persistence. And when we think about persistence, we have to also think about population size, not just growth rate. And because there is this demographic cost to selection that Haldane discussed similar ideas quite a while ago. Right, so if we actually look at population sizes in this particular experiment with the Daphne and the midge larvae, we see that populations with the predators, shown here in the triangles, have smaller population sizes and go extinct earlier than populations without the predators. So although the predator may be increasing adaptation at warm temperatures and increasing growth rates, it's not helping persistence of the prey. So in this case, the predator is not helping persistence, but what we wanted to ask is, will predators ever help the persistence of their prey? And if so, how will they do that? So to ask this question, we built a simple model that describes the change in prey density n over time as a function of birth rate, death rate, and predation. And each of these per capita rates can be functions of the prey's trait value and the prey's density. These are not functions, in this case, of the predator's trait value or the predator's density, because today I'm just going to be talking about a generalist predator that we assume is eating many other prey types, and thus its trait value and density is not as intimately linked to the prey dynamics. We also studied a specialist predator model, but that I won't talk to you about today, but we'll be happy to chat another time. Right, and so coupled with this density equation is the equation for the change in the mean trait value of the prey. And in this quantitative genetics world, this is the product of additive genetic variance and the selection differential, which describes the effect of selection, so the change in the per capita growth rate of the prey or the change in the prey's trait value. Right, so we start by assuming that we have this optimum phenotype for the prey, shown in the dashed line, and this increases over time. And in this case, the prey will evolve to track this environmental change and lag behind it by some amount. And we can think of this as increasing temperatures in the evolution of smaller body size if we wish to think about a concrete example as we go through this. Right, so in this case, the predator will help the prey adapt if it increases the rate of change in the mean trait value of the prey. That is, it pushes the prey trait value to be closer to the optimum. And we can break this equation down into some more meaningful terms, and we can work out the plausible signs of each of these terms. But for the purposes of this talk, suffice it to say that there are two ways the predator can help the prey adapt. One is when the predator selects in the same direction as the environment. So this is kind of like the midge example I talked about earlier, where basically the predator is removing the maladapted individuals and pushes the mean trait value of the prey towards the optimal. And we call this the selective push. And we can show with a simple example, both analytically and with simulations. Just the simulations are shown here today, but that populations with predators, shown in brown, remain better adapted than populations without predators, shown in blue. Now, there's another way, as I said, and this is perhaps the more interesting way that predators can help prey adapt. And this is when the birth rate of the prey depends on the prey's trait value and is also negatively density dependent. And so, in this case, increasing predation decreases prey densities, which increases prey birth rates, which effectively shortens the time between selective events in the prey. It's shortening generation time and speeding up turnover in the prey. And we call this the evolutionary hydra effect, with a nod to Peter Abrams' non-evolutionary hydra effect, where in this case, every time the predator removes a mythical prey head, the multiple heads that grow back are those that are enriched for those that are currently selected. so we're getting faster evolution in the prey through this evolutionary hydra effect. And we can again show with simulations that populations with the predators remain better adapted than those without. Right, so that's adaptation. I'd like to really emphasize that what I'm interested in is not just adaptation, but the persistence of the prey as a result of this adaptation. And so we need to define a measure of persistence. And so let this optimum trait value increase at a rate kappa. And a prey population in this environment will evolve to track this optimum, and its density will go to some equilibrium. We can measure this equilibrium lag below the optimum and the equilibrium density. And we say, let's increase kappa, and the lag increases, the density decreases, and we increase kappa further, and populations go extinct. And our measure of persistence will be the critical rate of environmental change, which is the minimum kappa that causes extinction. Right, so armed with this measure, we can then ask, when does predation help prey persist? And this occurs when the predator increasing predation increases the critical rate of environmental change. And again, we can break this into meaningful terms. But again, let's just stick with the main message here and say that predators can help prey persist when they increase the rate that prey adapt. And when this increase in adaptiveness overcomes the negative effect predators have on prey densities. And so again, with these same examples, first with the selective push, we can see that in a constant environment, predation is a bad thing. So the brown density is lower than the blue density. The population with predators has a lower density than those with predators. Those with predators have a lower density than those without. But in a changing environment, this increase in adaptiveness allows the population with predators to actually have a higher density. And the most exciting fact is that in an even faster changing environment, only the population with predators persists while the population without predators goes extinct. And so predators are helping persistence. And again, with the evolutionary hydra effect, we see the same thing, where in a constant environment, predation is bad, but in a changing environment, this increase in adaptiveness increases densities, and at faster rates of change, the evolutionary hydra effect promotes persistence of the prey when it would otherwise go extinct. Okay, so just to wrap that up, environments are changing, and they'll continue to do so as long as forever. The species interactions are going to be important for adaptation, particularly today we looked at predator and prey interactions. And what we've shown is that predation can help prey adapt and persist through two different mechanisms. One, through the selective push, where they're selecting in the same direction as the environment, and the second through this evolutionary hydra effect, which is effectively a shortening of generation time. And with that, I'd like to thank everyone.